You know how fast a quantity is changing at every moment? What's a quantity? Like height, temperature, volume, things that we measure, right? Things that scientists and mathematicians measure all the time. It could be any quantity. You know how fast that's changing at every moment. And then based on that, that information, we want to know how much of it you have. And that's what we call accumulation, right? So that the amount of that quantity accumulates as it's changing, right? So it accumulates, and that's what we're trying to come up with, is what is the accumulation function based on the rate of change function, right? So this is how fast a quantity is changing every moment. That's a rate of change function. How much you have at every moment is what we call an accumulation function. All right, so we said principle 1 was constant rate of change. So what does 60 miles per hour mean? What does 60 miles per hour mean? That's a constant rate of change. What's the meaning of that? Yes, sir? All right, every hour you travel 60 miles. Is that true? Is that a good meaning for that in this class? Tell me. You're shaking your head. What's a better meaning for that? Uh-huh. Right? Right. Right. So do you only know how far you go in 1 hour? Do you know how far you go in half an hour? Yeah, how far do you go? 30 miles. How far do you go in 2 hours? 120. How about 10 miles? 10 hours. 600 miles. You know how far you travel in any amount of time, right? That a constant rate of change, that number tells you how many miles would accumulate over any change in time. That's a broad meaning. And so how do we get that? Given a change in time? For any variation in time, we know we can get the variation in distance by multiplying it by that change in time by 60, right? 60 times a half an hour gives you 30 miles. 60 times 2 hours gives you 120 miles. Okay? So yes, you do go 60 miles every hour, but you know a lot more than that. You know how far or what variation distance you have in any amount of time. And that's so that this dy equals 60 dx, that equation frames the meaning of that constant rate. I'll keep asking you all semester. We'll get a rate, and I'll say, what's the meaning of that rate? For any change in the independent, multiply that rate by it, and you get the change in the dependent. Okay, the next one was a net accumulation function. What does this do? This tracks the amount of change for any value of x given a rate of change, right? So you have to have the rate of change. The net accumulation function tracks how much change you have at that rate. Okay, but then we said that realistic rates are often changing rates. So instead of the constant rate of the flag coming down, if he's pulling hand over hand, it may look something more like this, right? And so when you have a changing rate of change, coming up with this net accumulation function is more difficult, right? Because that was based on a constant rate. All right, so what did we do? We turned that changing rate function into a bunch of constant rates so that we could still use dy equals mdx. And are these changes 1 second each? What did we say? We did 0.35 seconds, but that doesn't phase us. What? Because if we have a constant rate, we know for any change in time, we can calculate the change in this case, height. Right? So these don't have to be changes of 1 second. They can be any, these intervals can be any width. And given the constant rate, we can come up with the change of height in that interval. Okay, so to start, let's just review. Take a look at, say, right here. So I put a green barbell around 6 quantities there, 6 values. So the first question is, where do those values come from, or how are they calculated? Each one, where do the values come from? How are they calculated, or where do they come from? And then 2, what are the meanings of each value? So this is just to get us warmed back up from last time. If you have that sheet, you can pull it out, but it's on the screen. So this is our initial questions here. So for all that situation right there, what's the meaning? Where do those values come from? How are they calculated, or where do they come from? And then second, what do they mean? What are they representing? What's going on in this table? Okay, everyone's got a partner. Everyone's talking to somebody. Derek is here to answer your questions as well. Everyone's finding someone to talk to. All right, tell me about the 2 and the 2.35, Kylie. What are those numbers? Okay. Good. All right. Awesome. So this is like the starting time and an ending time, which gives a variation in our independent variable, which is time, right? Excellent. Okay. The minus 0.6. Spin the wheel. Where is Mariana? Mariana here? Okay. What about the negative 0.6? Okay, yes, it was our best guess at an average. Good, yeah, so we kind of eyeballed, we said, hey, we think the average in that time interval is about negative 0.6. So then what do? In this pretend rate function, we said, we'll say it's constant rate. Instead of the changing rate in that interval, the blue, right, we'll just say constant rate through there. Okay, keep going, Mariana. So then what about the negative 0.21? And yeah, good. And how did we get that? Good, right? So this is like a dy. This is like a little variation in height of the flag. And where does that come from? It comes from m dx, right? It comes from, we got our constant rate, and we've got our 0.35 change in time. So we multiply them, and we get that little, the contribution in this time interval to the decreasing height, right? So the flag is gonna go down 0.21 meters, approximately, in that time interval. Okay, somebody new, last column. Where is Jizzing? Lou? Jizzing, yeah. Tell me about these, the negative 0.84 and the negative 1.05. Do you know what those numbers mean? Okay, the change in height of the flag. Okay, since when? So yes, that is a change in height of the flag. Since what point in time? What do you think? Anybody? Yeah.
Since 0.6 seconds.
Yeah, since this time, right? So this is accumulating changes, right? What did we do? To get these changes, we added up all the previous changes. We're keeping a running total, right? We keep accumulating changes. So then what is the negative 1.05? Somebody else, what's the negative 1.05? Yeah. Okay, what accumulation of what and since when?
Since 0.6.
So accumulation of?
The height that it's been, that the flags went down.
Yeah, so this is telling us that the height has gone down kind of like a total amount of negative 1, or like it's gone down 1 meter since 0.6 seconds. So all of these values are keeping the running total of how much height has decreased. How much the height has decreased. All of them are since 0.6, and so that's why we got these values by adding up all the previous changes. or previous variations in height. Okay, does that make sense? Any questions? So what did? We started with the actual rate, the real rate function, the blue graph. We created, in order to use dy equals mdx, we created this pretend rate function with constant rates. And this table is representing, kind of building, here's the pretend rate function, time versus constant rate. And then with these two columns, now we're creating how much we have, or our accumulated change in height for each time. Okay, does it make sense? Okay, so this is principle 4, pretend rate function, right? Pretend rate function. And so we're going to do kind of a pretend rate function part 2 here. We're going to do an alternate approach. Here. To the pretend rate function. And the way we're going to do that is instead of eyeballing and trying to find the average or the one rate that kind of best represents, instead of doing that, we're just going to say, let's just look at what the actual rate is at the left side of every interval. So we're going to start with that. So what I want you to do is, I want you to estimate the values. It's a little bigger. Okay, so I want you to estimate the values of the exact rate function, that's the blue graph, at the left side of every interval. So here I'm asking for numbers. You're estimating, you're kind of eyeballing what are numbers for the exact rate, the left side of every interval, and then compare with the person next to you to make sure you're on the right track. And then your second task after that, you're going to estimate all those values. So there's 1, 2, 3, 4, 5, 6, 7, 8 of those, 8 numbers. Those exact values that you estimated, those are unknown. Those are unknown, but they can be expressed exactly. And that's your next, number 2, that's the goal there. Express each of those values in such a way that they represent the exact value, even though we don't know what the exact value. Okay, does it make sense? So you're gonna be estimating the values of the blue function at the left side of every interval, and then expressing those numbers that you tried to estimate with notation that means the exact value. Okay, I'm going to start taking attendance. You're either making progress or you're getting help, okay? Making progress or getting help. Just 1 and 2. Make sure we're all on track.
I have -0.75.
And where are you looking to find that?
Where am I looking?
Yeah.
The very beginning of that interval.
Very beginning of that interval. So you're looking, and then where are you looking at the beginning of that interval? At the very function, and then you come over here and say -0.75. Okay, next one. Again, so here's the second interval. Are you looking at this point here? And then picking off the value? So right there, -0.75 meters per second. Okay, next one. -0.7. So instead of -0.75, now the value of the function on the left side of this interval is here. Does everyone see that? So -0.7. So that's just to check. Are you doing it right? Are you doing it right? And then after you get done with the 8 values, the estimates, then number 2 is write a representation. Write symbols that represents each of those numbers, but the exact value of each of those numbers. Okay? Keep going. No, just everybody keep going. Yeah, thank you. Good job.
So for number 2, write the math equation, not RH.
Function notation, yes, right. Oren. Sorry, I'm trying to move that. Oren. No Oren? Raymond Lee. Chauncey. How? Yi. Jordan. Maple. Ginseng. Thomas. Max. Phoenix. Jake Olson. Jake. Becca. Evelyn. I know you. I know you. Andrew. Alejandro. All right, Alejandro, did you get the first, how you would express that first negative 0.75? Did you get that? Okay. So how, we got this value here, negative 0.75, that we're estimating. What's a way to express that exactly? Mariana knows. Tell me your name again. Jake, right? He wants r sub h of 0.6. What do you think of that? Does that give us the value of the function at 0.6? Exactly. So that first negative 0.75 that we estimated, that was for this point here, the exact value of that is r sub h of 0.6. All right, let's go to this interval here from, what is this? 2.7, from 2.7 to 3.05. Who's got an estimate for the value at the value of that function at the left side? Somebody knew. What'd you estimate for the value? Yes, ma'am. About negative 0.2. Good. Okay, so that at the left side, we're right there on the function. Come over here, about negative 0.2. And that negative 0.2, that's an estimate of what exact value? Somebody else. How would I express that estimate? Yes, sir? R sub h of 2.7. The value of the function at the left side of the interval. So I'm not going to write out the whole thing, but you would have 8 estimates and then 8 expressions like this. R sub h of 0.6. What's the next one? R sub h of 0.95, etc. R sub h of 2.7, and the last one will be R sub h of 3.05. Any questions? So now I want you to sketch a pretend rate function based on those. Instead of the eyeballing and trying to get the average within the interval, instead of that, we're going to use these rates at the left side that we just were working on and let that be the constant rate for the whole interval. So can you sketch a new pretend function based on what we call a left-hand approach? The exact rates of change at the left side of every interval determines the constant rate for that whole interval. Can you sketch the function? Go for it. Okay, so our estimate for r sub h of 0.6 was what again? Negative 0.75. So watch, look. So I'm going to grab a constant rate and I'm going to put it down at negative 0.75. So that's what our pretend rate function will be in the first interval. I'm making a constant rate for the actual rate right there at the left side. Next interval. What do we say that the rate was at the left side of the interval? Negative 0.75 again, right? So we're going to have the same thing. I'm going to grab this constant rate of change and match it up with the left side. Maybe, yeah. So I'm matching it up with the left side. Next interval, where should the next constant rate go? Somebody knew. Where should the next constant rate go? Yes, sir. Right, so at the left side, the rate was negative 0.7, so I'm gonna let the rate be constant at negative 0.7 that whole way across. Next interval. Left side is the rate as the left side is? Negative 0.75 again. Come on. right? I'm looking right there. Next interval. What did you predict the rate, or say the rate was at the left side of the next interval? Zero? It's like negative 0.1, right? It's like right there, right? So in this interval, the rate of change at the left side, the rate of change is right there. It's a little bit higher than this one, right? So maybe negative 0.1. Is that what your estimate was? Some of you? Yeah, that negative 0.1 is a good estimate. So I'm going to take and make a constant rate at negative 0.1 for that whole interval. Next interval, constant rate at? Oh no. What happened? Okay. Just that. No. Next interval. This was our negative 0.2. Right there. Okay. This was our negative 0.2. Last interval. Again, negative 0.75. All right. Did I lose you? Does this make sense? If it doesn't, can you ask a question to help? What did I lose you? We're taking the actual rate on the left side of each interval and making that the constant rate through the whole interval. So that's what this is a new way of creating the pretend rate function. Rather than trying to eyeball an average, we pick off the rates on the left side to make that the constant rate. And then when we do it this way, we all get the same thing. We all get the same result. Okay, tell me what the exact value of this rate is right here. How could you express the exact value of this rate? Tell the person next to you. I'm going to express the exact value of that rate of change. Did you guys get it? How about one of you guys? What would the exact rate, the exact value of that rate be? Do you have an idea? So we're going to need the function notation, right? It's going to be r sub h of. It's going to be the actual rate from the blue graph at what value? At 2. R sub h of 2. That's the exact value of the rate in that interval. For the whole interval, right? So we're picking off this exact rate to be our pretend rate, but then for that whole variation of 0.35 seconds. Okay, any questions? Any questions? So let's see this in action here. So here's that very thing we just created, but now we think of it more as this situation is unfolding, right? It's happening, and that's what functions show. They show a dynamic relationship. There was some point in time when this flag was coming down, and as it was coming down, it was attaining all these different rates, and it was accumulating changes in height, right? So when you look at graphs, you want to think of them dynamically. They show covariation of two quantities. They're not just static like wires on the page, but they're actually showing a situation as it unfolded, okay? So here's what we said. And so now what about the accumulation function for this pretend rate function? Where will it start? So it'll start at 0.6. What will the value be at 0.6? This is now we're going to do the accumulation of height, the net accumulation of height for this pretend rate function, the blue one. At 0.6, what will the net accumulation of height be? 0, because the accumulation function we've been working on is the one starting from 0.6. And then what will happen in the first 0.35 seconds? The height will decrease at a rate of negative 0.75. So you'll get a linear graph because we're assuming a constant rate. And then what about in the next 0.35? Same thing. Our pretend rate function, we also said negative 0.75, right? So in those first two intervals, the height's going to go down at this constant rate of negative 0.75 according to our pretend rate function. Then what about in the next interval? What will the next part look like? The height will still be decreasing, but how compared to this? At a slightly lower negative rate, right? So you get another little line segment, but decreasing, but not as steeply, right? And then back to negative 0.75. And then what about the next segment? It's going to decrease at what rate? Around negative 0.1 or r sub h of 2. R sub h of 2, which is a low rate or a high rate? Low negative rate. So it's going to look pretty flat in that part. And then back to negative 0.75. And then I think we estimated the next one at negative 0.2 or r sub h of 2.7. So another kind of flattish one. And then finally negative 0.75 again. So here is the approximate accumulation function, or tracking the running total of height decrease for the pretend rate function, the blue one. So what we want is we want to write this as this function as a formula. So we can understand the graph, we can see where that graph came from, but how do we write, and we call this, so the black function came first. Black function came first. That was r sub h. And then our pretend function was the blue one, and we called it one r. And then the purple one, I got all the colors today. The purple one is our approximate accumulation function based on the approximate rate. So what we want to do is try to come up with a formula for the approximate accumulation function. And to do that, what we can do is we can look at, say, pick a point here, 2.15, time 2.15. What are the exact coordinates of that point? What are the exact coordinates of that point on our pretend rate function? 2.15. And now I want exactly. How can I express that rate of change exactly? Where did that rate come from? Yeah, don't. What's that? Okay, it's not A. A is going to be this one over here. So we want for this one, where did this come from? R sub h of 2.15? Okay, r sub h of 2.15 is this value down here. Is the value of the function there. Where does this rate come from if you get to 2.15? R sub h of 2, right? Because we said we picked off the rate at 2, and we said that's the constant rate for the whole interval, including the time 2.15. So it's r sub h of 2, right? Because r sub h of 2.15 is now back down here again. But we assumed a constant rate of r sub h of 2 for this whole interval. Okay, so what I want to do is I want to try to write, how would I write a of 2.15? So to come up with a formula for a of x, we'll do that by looking at one example, a of 2.15. What would it take, what would it look like to get 2.15? This value right here, this is the 2.15. So whatever that is, where does that number come from? We want to write out an expression that's calculating that value of a at 2.15. So what is that? That's all the accumulated change in height of the flag since 0.6. How would I get all the accumulated height of the flag, changes in height of the flag since 0.6? Where does that come from? Where does this, the y value of this point, come from? What do we do to do that? Yes, sir? Accumulation of dy, right? In every interval, we know what the dy is. And then this function gives a running total of that. Accumulates everything from previous plus the new change. So how would I start? What would I do? What's that? No, let's just write it out. We're going to write out this one. What's that? So I want to get, so I've got a dy from this interval and a dy from this interval, a change in height from this interval, a change in height, etc. So I want to write this out. Let's see.
-0.35 times 0.95
So that's the rate in the first interval. And then what variation of time? 0.35, right? So the rate in the first plus the time. Okay, then? Right? Right? That was our negative 0.7, right? So what am I doing? M dx plus M dx. I'm accumulating the changes from each interval. This should make sense. This is exactly what we did in the table, too. Right? This is exactly what we did in the table when we just did it vertically. Okay? Then the negative 0.7 times 0.35. So I'm going to actually do plus the opposite, right? Plus negative. Plus negative. Okay? And then plus what? Negative 0.75 times 0.35. And does that give me my estimate for 2.15? I got a little bit more, right? What's the little bit more that I have? Plus what? Negative 0.1 times 0.35, right? I only go partially through this interval. I don't go all the way. I don't have a full completed interval. I only go partially to 0.15. Do you see that how that's an approximation for a of 2.15? M dx for the first interval, dy, plus M dx for the second interval, plus M dx for the third, plus the fourth, and then a little bit more, a partial interval in the fifth. And totaling all that up is getting our running total of what that a value is there. I want you to rewrite this now using all exact, make it exact. Rewrite this expression and make it exact. Go. Rewrite that expression and make it exact. So where's Skylin? Did you get this?
The exact.
Yeah.
So it would be R sub H of the first time interval 0.6
Good.
times dx.
Good. And actually we're going to call that delta x, okay?
Yeah, and then we just repeat that, so it would be plus R sub H of 0.95 times dx plus R sub H 1.3 dx plus R sub H 1.65 dx, and then plus R sub H of 2, and then times 0.15.
Okay. Good. All right, so this fixed interval that we picked, we're going to call that delta x, Greek delta, triangle. When we get into the current interval, we have this variable amount, this amount of variation that's changing in the current interval, right? It starts at 0, and it ends at delta x. And then we get to the next interval, and that amount of variation starts at 0 and goes to 0.35. So right now, that amount of variation in the current interval is 2.15. What do we call that? Remember? That variation in the current interval is what we call, that's our dx. That's our dx. The fixed interval width, the fixed variation that we start off with and it never changes, that's the delta x. That's the 0.35. So good. So this is what you should have written. the first exact rate times the 0.35. The second exact rate times the 0.35. Running total, accumulating. Quantities accumulate as time goes by, right? And we're accumulating bit by bit. So this is giving us a form to think about how we would write this approximate accumulation function. What do you notice? There's kind of two parts to it. There's all this adding up all these dy's for the what we call completed intervals, full delta x with intervals. And then we add on a little bit more for however far we've gone in the current interval. So when we write a sum, and it's the same thing over and over again. Look, it's an r sub h times delta x, and r sub h times the delta x. So we can do that shorthand by writing what? We can just write that once. R sub h, say of x for the ith interval, delta x. Just write it once, because they're all the same, right? And then, what do we use to show that we're going to add many of those together? That's what the Greek sigma is for. All that's saying is, it's not, I'm here to scare you. It's just saying, hey, look, I'm just going to add up a bunch of these. They all look like this. I'm going to add a bunch of them up. So I'll just write it once. And then the sum means we're going to sum a bunch of those up. Where I is going to start at 1 for the starting interval, and then it's going to end at the number of completed intervals. So I will start at 1, and we'll get this term. Then I will be 2, and we'll get this one. And then I will be 3, and we'll get this one. And then I will be 4, and I'll get this one, and we'll add those all up, right? But then we got a little bit more, plus the r sub h for in the current interval, so I'll call that x sub cur, r sub h x sub cur. But this one is times the partial amount, however much we varied in the current interval. So not a full dx. Sorry, not a full delta x. All right, so this gives us a form for that function a that we graphed over there. It's the sum of all the dy's, the changes in height for the completed intervals, plus a little bit more change in height from the current interval. Okay, so we're getting kind of dangerously close here too. We know how fast something is changing at every moment. We want to know how much we have. We've got a nice a skeleton here of this. You know how much you have. You want to know how much you have at every moment, right? This changes in height of the flag. Questions on where that came from? Did it make sense? Okay. So what about this approximate accumulation function? Good? Do you remember what we initially drew? Can you see that there? Remember what we initially drew sketched for the exact accumulation function? So not exact, right? It's not a match. So I want to do better. I want to get a better approximate accumulation function so I think of a way to get it exactly down the road. But for now, just how would I get it to be better? If I made, go ahead, yeah. If you made smaller delta x intervals, what would happen to the rate function? The rate function would be more accurate. And if the rate function is more accurate, then, so watch, here's a shorter delta x interval. And it made a new left-hand version of the rate function. And here's, make it even smaller. Do you see that this constant rate function for smaller intervals now? It's doing a better job reproducing that. Look at that. So this is 0.0257. And then we can make it super small. And every time we make that rate, those intervals smaller, what would happen to our approximate accumulation function? Watch, here's a smaller interval, smaller interval, smaller interval, smaller interval. Till now, you can't even see it on there. I'll turn it off. Let's see. You can barely see the difference between the approximate rate, right? The approximate rate and the exact rate. It's there though. The approximate rate is there. It's just a bunch of tiny little horizontal segments that are doing a really good job matching the exact rate, and then therefore our approximate accumulation is going to do a really good job of creating whatever this exact accumulation of height. So just quickly here. Pretend rate function. With a pretend rate function, we can get this approximate net accumulation function. And then principle 5 would be make more smaller intervals. Better pretend rate function means a better net accumulation function. Okay, you'll be in suspense till Wednesday. How do we get the exact accumulation function? Have a great weekend. Check Canvas for all the announcements and homework. See you Wednesday.